All right, hello everyone, and welcome to Lesson 10 for our Unit 8 AP Chemistry curriculum. Today we are going to be talking about buffer capacity. So buffer capacity is basically how well a buffer can resist changes in pH. We already know that buffers resist pH changes when small amounts of acid or base are added, but the deeper idea is the amount of buffer components matter. So if we increase the concentration of both the weak acid and its conjugate base, while keeping their ratios the same, the pH will also stay the same, but the buffer becomes much better at neutralizing added acid or base. So that's what we mean by increasing buffer capacity. The composition of the buffer is also really important. So if a buffer has more conjugate acid than it does base, it's better at neutralizing added base. And if it has more conjugate base than acid, then it's better at neutralizing added acid. So first, let's look at this idea on a very simple level. So say we have a weak acid buffer with a pKa at 4.74. And looking at the particle diagram here, we can see that we have, let's just call it out of 1 liter, so a concentration of 4 for our weak acid and a concentration of 6 for our conjugate base. And when you solve the pH with the Henderson-Hasselbalch equation, you get a pH of 4.91, which should make sense because we know at the half equivalence point, when we have equal amounts of our weak acid and our conjugate base, we will have a pH of 4.74. However, in this specific example, at this point in time, we have more of our conjugate base than we do our weak acid. So we're going to expect a higher pH in this specific sample of buffer. So looking at this buffer solution, because we have more conjugate base, this means that this buffer can neutralize more acid than it would be able to base. So now let's compare what happens if we were to dilute the buffer or minimize the number of weak acid and conjugate base particles we have. So remember, in our original, we used the Henderson-Hasselbalch equation with the concentration of our 6 conjugate base particles and 4 weak acid particles, and that gave us a pH of 4.92. Okay, now if we were to dilute the buffer, and in this case we're diluting it by half, so instead of 6 concentration for conjugate base, we have a concentration of 3, and instead of 4 for our concentration of weak acid, we have a concentration of 2. So let's plug that into Henderson-Hasselbalch and see what happens to pH. And again, it's going to have the same pKa because it's the same weak acid, so that's not changing. So plug that into your calculator and see what you get for pH. Now hopefully you get the exact same pH. And this is really important for this lesson. So if you have the same proportional concentration of your weak acid and conjugate base, the pH is going to be the same. However, if you are adding small amounts of acid or base to these two different buffer solutions, this buffer is going to be able to neutralize a lot more acid and base compared to this buffer, simply because there are more particles there to neutralize. Buffer capacity is the amount of strong acid or strong base that a buffer can absorb without a large change in pH. It's basically a measure of how effective the buffer is. What determines the capacity is the actual concentrations of the weak acid and conjugate base that are present. The more of these components you have, the more acid or base the buffer can neutralize. So comparing these two buffer solutions, we have 1 molar acetic acid and 1 molar sodium acetate with 0.1 molar acetic acid and 0.1 molar sodium acetate. So they are the same proportion of concentration, meaning if I am plugging into Henderson-Hasselbalch for my top buffer, it would be 1/1. And for my bottom scenario, it would be 0.1/0.1. Both of those give you a value of 0 for this portion of Henderson-Hasselbalch, which means the pH is equal to the pKa, which should make sense because you have equal amounts of your weak acid and your conjugate base. So even though they have the same pH, the top solution has a much higher concentration of both species, which means it can absorb way more HCl or NaOH, which means it has a higher buffer capacity. And I just want you to add in your notes this green box here. Just remember, when thinking about Henderson-Hasselbalch equation, if all you're changing is the amount of weak acid and conjugate base, but the ratio is staying constant, then your pH is going to stay the same. The only thing that you're changing is how much acid or base that the buffer can neutralize, so the capacity. The key idea for this lesson is that the more dilute your buffer is, the less effective it is at resisting change in pH. In other words, lower concentrations mean lower buffer capacity, and that also works on the flip side. If you increase the concentration of your buffer while keeping the ratios the same, the pH stays the same, but the buffer becomes much better at neutralizing acid or base. Looking at the graph, you can see that in the middle region, the buffer resists changes in pH, which is why there is not so much of a change when we add acid or base. That's where it's working the most effectively. But once you add too much acid or too much base, then that buffer capacity is exceeded and the pH starts to change more rapidly. So key takeaway, stronger, more concentrated buffers can handle more acid and more base before reaching that breaking point. If a buffer has more weak acid than conjugate base, it's better at absorbing added base because there's more acid available to neutralize that hydroxide. On the other hand, if a buffer has more conjugate base than the acid, it's better at absorbing added acid since there's more base available to react with those H+ ions. The graph on the right kind of helps us visualize this. So looking at this graph, we can see our pKa value in pink in the middle there. Remember, this is when the concentration of weak acid is equal to the concentration of conjugate base. Now, clearly here in this buffer, we are at a pH of a little bit higher than our pKa, which means we have more of our conjugate base than we do our weak acid. And because we have more conjugate base in the buffer, that means we can neutralize more acid within the buffer. All right, let's do an example. A student obtains 250 milliliters of a buffer containing 0.6 molar hydrofluoric acid and 0.2 molar sodium fluoride. Can the buffer withstand more added acid or more added base? So first, let's figure out what type of buffer we have. We know we have a weak acid, which is HF. And we know we have 0.2 molar NaF, which has our conjugate base F minus. So this is our conjugate acid-base pair, which is the buffer itself. Now, from the information given in this problem, we see that we have 0.6 molar of our weak acid, and we have 0.2 molar of our conjugate base, which means we have significantly more of our weak acid. And because we have more acid than base, that means we can neutralize more base. So the answer to this question is this buffer can withstand more added base than it can added acid. How do the pH and buffer capacity of buffer X compare to those of buffer Y? So looking at these two buffer solutions, we can see that both of them have the weak base, NH3, and the salt that includes our conjugate acid, ammonium, or NH4+. So ammonia is our weak base, and ammonium is our conjugate acid. Now, hopefully you can look at these and say, oh, they're equal concentrations of weak base and weak acid for both of these buffers, which means they're going to be the same pH. But I am going to show you one more time why that is. So let's first start with buffer X. So we're working with a weak base, so we're going to have a pKb value, which means we are going to be solving for pOH. So let's start off with buffer X. We have a pKb of NH3 at 25 degrees Celsius is 4.74. Then we have the log of the concentration of our conjugate acid, which is 0.1, over the concentration of our weak base, which is 0.1. Now, this is obviously equal to 1, and the log of 1 is 0. So that means our pOH is equal to the pKb, which is 4.74. So if we wanted to solve for pH, we would just take 14 minus 4.74. And you get a pH of 9.26. Now let's do the same thing for Y. So again, we have a weak base, so we're going to be solving for pOH. Our pKb is 4.74. And then we have the log of the concentration of conjugate acid, which is 0.5, over the concentration of weak base, which is 0.5. So again, this gives us 1. A log of 1 is 0. So pOH is equal to pKb, which is 4.74, which means our pH is 9.26. So as you can see here, as long as our ratios in this section of Henderson-Hasselbalch are the same, it's going to give us the same, in this case, pOH. Now moving on to buffer capacity. So first, we found out the pH is going to be the same in buffer X and buffer Y. Now let's look at buffer capacity. Remember, the more you have, the more acid or base it can neutralize. So the higher the capacity. So looking at buffer Y, we clearly have a lot more of our weak base and our conjugate acid, which means it has a higher buffer capacity or can take on more acid or base without a big change in pH. A solution is prepared by combining 1 liter of 0.5 molar HClO2 with 1 liter of 0.5 molar KClO2. The pH of the solution is 2. If the solution was prepared by combining 1 liter of 2 molar HClO2 and 1 liter of 2 molar KClO2 instead, what would be the pH and buffer capacity of the new solution? So first, let's look at pH. Remember, if it's the same ratio of weak acid and conjugate base, it's going to have the same pH. And as you can see, in our original solution, we had 0.5 and 0.5, so equal amounts of HClO2, which is our weak acid, and KClO2 minus, which is our conjugate base. So equal amounts. So let's look at our new solution. We have 2 molar HClO2 and 2 molar KClO2, which means again we have equal concentrations of our weak acid and our conjugate base. So because they are equal concentrations, the pH is not changing. So the pH is going to be 2. And then for buffer capacity, obviously we are quadrupling our concentration of weak acid and conjugate base, which means we're going to have a much larger buffer capacity because we have a lot more of our weak acid and conjugate base. All right, let's wrap up this lesson with a practice FRQ. A student wants to prepare a buffer solution starting with 1 molar propanoic acid solution. The student has access to 2 other solutions, 1 molar potassium propanoate and 1 molar potassium hydroxide. The value of Ka for propanoic acid is 1.34 times 10 to the negative 5th. Briefly describe how the student can prepare a buffer solution with a pH of 4.87 using 1 molar solutions. So before we do that and try to figure out how to prepare our buffer solutions, we need to figure out what is our concentration of weak acid compared to our concentration of conjugate base. And we're going to do that by solving for the pKa. So remember to solve for pKa, that's going to be the negative log of your Ka value. So we are given that in this case, so negative log of 1.34 times 10 to the negative 5th. And when you put that in your calculator, you get a pKa of 4.87. And because our pKa and our pH are equal to each other, that means we know that our concentration of weak acid is equal to our concentration of conjugate base. So now let's figure out how to prepare our buffer solutions. So for the first part, we are given 2 solutions of 1 molar propanoic acid and 1 molar of the salt that includes our conjugate base. So because we only have 1 conjugate base in this salt formula, it's a 1-to-1 ratio, which means I need equal solutions or equal volumes of these 2 solutions. All right, so remember our buffer is defined as a solution that has the weak acid and the conjugate base. So in part I, that was pretty simple because we had our weak acid and we had our conjugate base. But in the second part, we are not given that. We're given our 2 reactants, our acid and our base, that are going to neutralize each other, and we need to figure out how much we need of each to get equal concentrations of weak acid and conjugate base. So let's go ahead and start out with our equation. So we have HC3H5O2 plus KOH. We know we're going to form water and potassium propanoate. So we know KOH completely dissociates because it is a strong base, and potassium propanoate is going to dissociate because it's a salt, and having potassium in it tells us that it's soluble. So clearly our spectator ion is going to be potassium. So rewriting this as our net ionic equation, we're going to have HC3H5O2 plus hydroxide reacts to form water and propanoate. All right, so why does this matter? We need to figure out how much potassium hydroxide we need so that when it neutralizes with propanoic acid, we're left over with equal concentrations of our weak acid and our conjugate base. Now, for ease of understanding what I'm talking about, let's just say we're going to react 1 mole of each. So I have 1 mole of my strong base reacting with 1 mole of my weak acid to produce 1 mole of my conjugate base. So I know the buffer will have 1 mole of conjugate base, which means I need to be left over with 1 mole of my weak acid, which means I need to start with a total of 2 moles of my weak acid, so that when I mix with my hydroxide to form conjugate base, I still have equal volumes left over at the end of weak acid and conjugate base. So your response should look something like this. Combine 1 molar propanoic acid and 1 molar potassium hydroxide in a 2-to-1 ratio, respectively. And if you wanted to give it a volume on either one of these options, you could totally do that. So you could say like 1 liter for part I. You could say 1 liter of 1.0 molar propanoic acid and 1 liter of 1 molar potassium propanoate. So you can do that, and then on the bottom you would do 2 liters of 1 molar propanoic acid with 1 liter of potassium hydroxide. So if you would rather put a value on it, that would be totally fine. That would still get you the points. All right, part B of this FRQ. A drop of strong acid is added to a buffer solution prepared as you described in part A. Write a balanced net ionic equation for the reaction that helps to explain why the pH of the solution remains essentially constant after the addition of a strong acid. So we know that our conjugate acid-base pair is propanoic acid, which is HC3H5O2, and our conjugate base is propanoate, so C3H5O2 minus. So this question is asking why the pH of the solution remains essentially constant after the addition of a strong acid. Well, we know, for example, one of our strong acids would be like HCl or HBr or HClO3. They have a hydrogen, so we are introducing an H+. And when we're introducing an H+ or an acid, it's going to be reacting with our base. So if we wanted to write out our net ionic equation, that's why I separated this from HCl or whatever strong acid you want to use, we would write our net ionic equation as the conjugate base, because that's what's reacting with the acid, plus our H+ ion, and then it would form our original weak acid. And that is our answer. All right, and last part of this FRQ, the student makes another buffer by mixing together 150 milliliters of 1 molar propanoic acid and 100 milliliters of 1 molar potassium hydroxide. The student claims that the pH of this buffer solution will be lower than 4.87. Do you agree or do you disagree with this claim? So first of all, we know that pH is equal to the pKa at the half equivalence point, and we know that the pKa is 4.87. So at a pH of 4.87, we have equal concentrations of our HC3H5O2 and our C3H5O2 minus. So equal concentrations. So what we need to do to figure out if the pH is going to be lower is we need to figure out what we have more of. Do we have more of our weak acid or do we have more of our conjugate base? And that will tell us what the pH will be. So we already wrote out the ionic equation for this, so I'm going to go ahead and just rewrite that. So we have our propanoic acid with hydroxide ions react to form water and propanoate. All right, so I am starting with 1 molar and 150 milliliters of propanoic acid. So in order to get moles of that, I have 1 molar times 0.15 liters. So I am starting with 0.15 moles of propanoic acid. Then for hydroxide, I have 100 milliliters of 1 molar. So that's going to be 1 molar times 0.1 liters. So it's going to be 0.1 moles of hydroxide. So because hydroxide is limiting, we are only going to be using 0.1 moles to make our conjugate base, and that's going to be a 1-to-1 ratio. So we're going to make 1.1 moles of our conjugate base. So now that we have moles of conjugate base and moles of our weak acid, we can solve for concentration of those if you needed to move on, but I guess we don't really need to move on at this point. So as you can see, we have more of our conjugate base than we do our weak acid. And because we have more of the conjugate base, that means we're going to expect the pH to be higher than 4.7. So it says, do you agree or disagree with the claim? The first thing you should be doing when you're answering a question like this is stating whether you agree or disagree. I would be starting with that and boxing it in personally, and then justifying it with what we just said. So something along the lines of the buffer contains a higher concentration of the conjugate base, and therefore the pH of the buffer would be higher than 4.7.